Hello everybody, welcome back to our Mathematics A&A Friday. Today we talk about AHL 1.12 Mathematical Induction. Very powerful tools but really hard to use. So in this video I will show you some important tricks. Use it, work hard on the past paper. I'm sure you can get used to it. Okay? And this is an additional high level that we pay attention to. So we are still on the topic 1, the number and algebra AHL. Okay, nearly at the end. Okay, we are on a mathematical induction. Okay, and then proof by mathematical induction. The game is 1 by 1 proof. Okay, no, proof 2 times, and the whole thing will be proved. First is very easy. First, prove that the statement is true for n equal 1. Fairly essential step. It is the smart way to define a statement, but in the past paper they define a statement for you too. So it's just want you to appreciate they define a smart statement. Easy to start with number 1. Okay, step in proving about mathematical induction, the standard way. Okay, A, B, C, D, A, B, C, 3 step. Okay, and a trick. Okay, the first step is to prove that the statement is true for n equal 1. This is a fairly easy way. No problem. The other is assume the statement is true for n equal k. No problem. You just assume it and then list it out. N equal another integer k. And then show that if it is true for n equal k, and then it is also true for n equal k plus 1. So k becomes k plus 1. So what are you doing? I prove that 1 is correct. And then I prove that the next one will be correct too. So 1 correct, 2 correct, 3 correct, and so on. So all positive integer n, the statement is true. Very smart way. I appreciate it. Okay. Finally, copy the following statement as a conclusion. True for n equal 1, and if true for n equal k, then true for n equal k plus 1. By mathematical induction, the statement is true for all n belongs to the positive integer. That's it. Excellent. The trick is how to do also true for n equal k plus 1. The trick is a sum to m plus 1 terms. Okay, is equals to sum to m terms plus the m plus 1 terms. For the sum to the m term, you can use the assumption place to work on it. You got it? Try to do this one. Try to prove this summation equals 1/6 of n plus 1 and 2n minus 5. Really hard, but follow our step. Prove that n equals 1 true first, and then assume n equals m is true. Prove that n equals m plus 1 is also true. Try to work on it. It's really hard, but experience the difficulty will let you appreciate the solution better. Okay? Bring a paper and work on it. Pause the video. Welcome back. I'm sure you work hard on it. You have some experience on it. Okay, you got the obstacle and see how can we pass through it. So first of all, n equal 1 is very easy. Right hand side. Okay, substitute n equal 1 is minus 1. For the left hand side, substitute n equal 1 sum from k equal 1 to 1. So that's one term. Okay, also negative 1. So the statement is true for n equal 1. So assume the statement is true for n equals m. Okay, so summation to m, 1/6 m plus 1 to m minus 5. Okay, correct. Okay, assume they are correct. Okay, and then we work for n equals m plus 1. So starting from the left hand side, remember the rules. Okay, summation to m plus 1 is summation to m. Copy it here. Plus the m plus 1 term. So m plus 1, k becomes m plus 1, k minus 2 becomes m plus 1 minus 2. And look at the two terms. Okay, take out as many common factors as possible. Take out m plus 1 and take out 1/6. And what's remaining? 2m squared minus 5m, 6m plus minus 6. And then from this thing, look at your target. Your target is here. Substitute m plus 1. So m plus 1. Okay. So I should have a term m plus 2. And also to have a term 2m plus 1 minus 5. So see if you can do it. Obviously, you need to factorize it. Okay. Just one way to factorize it. Okay. To simplify it, 2m squared plus m minus 6. Factorize it, 2m minus 3m plus 2. Okay. And then think about how to make it like this form with n equals m plus 1. I got it, m plus 2. Excellent. But you write it clearly, m plus 1 plus 1. Okay. How about 2m plus 1 minus 5? Yes, actually it's 2m minus 3. So we did it. So the statement is also true for n equals m plus 1, true for n plus 1, n equal 1, and if true for n equal m, also true for n equal m plus 1, you start the engine 1, then 2, then 3, then 4, then all the positive integer are proved. So by mathematical induction, the statement is true for all n belongs to separates, okay? Positive integer. Got some experience on it? Take the challenge. Next one. Prove this thing left hand side equals right hand side. The trick is, where is the first? What's n equal 1? Think about it. Look at the pattern. Okay. Welcome back. You see the trick is, these terms add together is the first one. 1 over a plus 1 minus 1 over a is the first one. And then each term is adding minus 1 to the power n, 1 over a n. Okay. So this is the first term, not 1 over a plus 1. So you got it. Okay, left hand side is 1 over a plus 1 minus 1 over a is equal to negative 1 a plus 1 are exactly the same, right? So n equals 1 is proved. Assume n equals m are correct. Okay, remember summation to the mth term. Okay, correct. And then summation to the m plus 1 term. So one extra term. So add this thing to the m plus 1 term. And look at them. Common factor. Minus 1 m plus 1. Why? Because the result should be this m plus 1. Okay. So a also m plus 1. A plus 1. Okay. Get all the thing ready. So this thing is 1. Then the result will be there. So get the thing. Okay. Negative a. This thing remains is a plus 1. Oh, miracle. Really cancel out minus a plus a. So this is right hand side. So you did it. Okay. Miraculous. Okay. So you did the thing. Okay. So remember the trick. Summation trick, and look at your target when you do the taking out the common terms. Okay. Prove my direct operation. Sometimes mathematical induction is too complicated. In the exam, be careful. There may be some simple way to do so by direct operation, so you save a lot of time. Especially when you look at the past year, the marks is too little. It shouldn't be for mathematical induction, then use other way. Okay. Maybe just left hand side operation, and then you can go to right hand side. Okay. Of course, for this thing, just like what we have shared before. Okay, start from the complicated side. For example, this one, prove this one, an equals 1 plus square root m to the power n. Prove that an plus 2 equals 2an plus 1 plus m minus 1an. Wow, very complicated. But starting from the right hand side, you can find out it can be proved by direct inspection to the left hand side. Pause and work on it. Welcome back. See if you're right. Okay. Yeah, starting from the right hand side. Okay, everything. And then a definition, right? Definition. And take out the common term, okay, to the power n. And the remaining is 2 plus 2 square root m plus m minus 1. Try to make it simplify a little bit. And look at this thing. How can I do this thing? Remember 1 plus square root m. It is 1 plus square root m square. Right? Yeah, so you got it. You got it. Okay, so it's 1 plus square root m, m plus 2. So it's a m plus 2. It's the left hand side. You got it? Very funny. Okay, then I prove another example. The first is very popular in the past way, but prove divisible. What do you mean by divisible? It means that the ratio of the divisor and the divisor is an integer. They always have a ratio, but if it is an integer, the ratio is an integer, then it is divisible. So our task is to prove the ratio to be an integer. Okay. So prove an is divisible by bn, means an is equal mbn, and m is an integer. So our target is not to prove that they have a ratio. They always have a ratio. Right? To prove m is an integer. And then prove a1 is divisible by an, and prove is ak is divisible, then ak is also divisible. It's a mathematical induction. You learn it? Yes, then start to do it. Okay. Prove that the h to the power n plus 6 is divisible by 7 for any positive integer n. How can I prove it? Mathematical induction. Prove n equal 1 correct, and then assume n equal k, and then prove n equal k plus 1 also correct. Okay. And that's it. Pause and work on it. Welcome back. It's really hard, right? It's the first time you do it. Look at the marking scheme here. Then work on other passive. You can learn it quick because I trust you. Okay. So for n equal 1, okay, yes, on the left hand side, okay. 14, oh, good, divisible. And then assume it is divisible by 7. Remember, divisible by 7 is multiplied by integer k. The main point is k is an integer. You can always write something as a 7k, right? But k is an integer, is divisible. And then work out for the next term, okay? And then find it out. And then h to the power m, I look at here, 7k minus 6, okay, substitute inside. And it's still a little bit far away, so just combine them, you can see this thing. And then to see the last two term, minus 48 plus 6, what's this? Minus 42, oh, divisible by 7. So the whole thing is divisible by 7 because it's multiplied by 7 of an integer because 8k minus 6 is an integer. Of course, k is an integer, right? 8k minus 6 is also an integer, so it's also divisible. Mathematical induction, you prove it is true for all m belongs to the set plus. And then for solution, okay, function, prove that. What? So think about it. Do you need mathematical solution or some direct inspection? Welcome back. See which way it works, okay? Yes, mathematical induction. Direct inspection is hard, okay? So for n equals 1, easy, right? For n equals for this one, f1 plus n is a to the power 1 fx. Yeah, it says so. It's really this assumption, right? True for n. And then assume it's true for a n equals m. And then consider m plus 1 starting from the left hand side, okay? So m plus 1 plus x. So how to make it? I know this way. So 1 plus something. So move the 1 to the top, okay? Okay, so it's 1 plus m plus 6. So it is a f m plus 6. Ah, I got it. This one I got it. It's a n. So a n plus 1. Oh, excellent. Equal right hand side. So you got it. So when you do it several times, I'm sure you are a quick learner. You start to got the trick. And then we have two more tasks, okay, prove binomial theorem. Prove binomial theorem is a good example of you need to manipulate NCR, okay, combination, really hard, okay, in mathematical induction, okay. For example, proving a binomial theorem, okay, binomial theorem is like this, okay, so prove n equal 1, but be careful, it's m equal 0 to 1, so two terms, okay. And really mark it clearly, m equals 0, 0, m equal 1, 1. And then it's a plus b, oh, miraculous. So it's a plus b to the power 1. Left hand side. Excellent. So true for n plus 1, n equal 1. How about assume n equal k is true and then work for n equals k plus 1. I know, 1 more a plus b. So multiply inside. There are two terms with this coefficient a to the power m, b to the power k plus 1m minus m, okay. So the two coefficient is km and km plus 1. And how to manipulate these two is hard. It's just definition. Taking out the common term and see what's inside. K plus 1. Oh, so it is k plus 1 cm. So all the terms has this thing and actually it is a summation. So you prove it. Yeah. So probably we don't need to prove a binomial theorem in the exam, but if you want to prove about similar thing, you need to manipulate this combination stuff. Okay, just work it out from definition. So prove a De Morris theorem, but I'm sorry, I just think about this important theory to be proved, but I'm sorry, IBDP has cut out some of the trigonometric function properties. So the last step, we don't know it. Okay? We just have to accept it, assume it is true. Okay. So De Morris theorem is like this: so cosine theta plus I sine theta to the power n is cosine n theta plus I sine n theta is marvelous theorem, hard to prove, but it can be proved by mathematical induction. Assume n equal 1. Okay. Correct? Yes. Cosine theta plus I sine theta. Right hand side the same. So the same. True for n plus 1. N equal 1. So assume it's true for n equal k. Okay. K. And then a k plus 1. So one more term. So what do we do? Substitute this one and then do the expansion, right? And then to the red one, you see the real part and the imaginary part. And if you are, and in the previous curriculum of mathematical and mathematics, okay, IBDP, you know, we have this thing in the syllabus, but now they cut it off. So these two can add together, and these two can add together. Sum of trigonometric function, and this exactly is the right hand side. So try to look up on the internet. This combination of trigonometric function is correct. Okay, it's an identity. Okay. So compare two sequence. Okay, when you want to compare two sequence, sometimes it's harder, but one is bigger than the other. Actually, we can change the formalism as a minus them, subtract them to the larger than 0. If yes, then A1 is larger than B1. Okay, that's the trick. Okay, try to work on it. Okay, if A1 is larger than B1, and then well, complicated stuff. Okay, so that AN is always larger than BN. Try to work on it. Mathematical induction or direct inspection. Pause the video and come back. Welcome back. Direct inspection, yes. So A1 minus B1 larger than 0, yeah. And then we do work on the AN minus K, AN minus 1, okay, and then do some changing of the position, and then you got this one. And then N is N minus 1 times K. So if this thing go on, then what we get? K N minus 1, A1 minus Bn. And A1 minus B1 is larger than 0, right? So this is larger than 0. So the whole thing is larger than 0. So AN is larger than Bn. So we prove it by direct inspection. You got it? And then how can you do the opposite? Sometimes maybe you can assume the opposite. And then if the opposite statement is a contradiction, and then the original statement is proved. But I never seen this happen in IBDP pathway, but it's just a free run, okay? We seldom use it, okay? Honest. And there is a counter example, because sometimes you can use a counter example to show a statement is not always true, okay? Just try the several values 0, 1, 2, 3, and then you find out quickly that you find a counter example. The concept is that not always true is incorrect, because as a statement, it must be always true. Okay? If you find the statement is wrong for one situation, then the statement will be discarded. So easy to discard a statement. Okay. Okay, a sequence is like this. Okay, here's all the thing. Is it divisible by 3? So we can work for n equal 1, 2, 3. N is 1 is divisible. How about 2? How about 3? Try to work on it. Welcome back, you got it. Where did you stop? I stopped at the third one. A2 15, yeah. A3 19, oh, not divisible already. So the statement is incorrect. You don't need to work anymore. Just one counter example is enough. So thanks for going through with me. This is a wonderful experience for sharing mathematical induction with you guys. Okay, it is a logical game, really fascinating. So go to internet, textbook, past paper, work on more example past paper, and you will be amazed that the theory is so sophisticated and you can do it. Okay, see you for next Friday. Bye.